one thing I want to talk about really quick is why we use accelerometers. A lot of the reasons we use accels is to measure vibration. If you have a part that's behaving poorly and you want to see what frequencies it's vibrating at, you can measure the vibration. It can be used to measure speed and tilt angle. These are actually really important in your cell phone. There's a lot of tiny accelerometers in there that'll help guide your GPS. If you ever wanted to know how that was working, you actually have a tiny accelerometer in your phone that'll tell you exactly these two things based on the acceleration. It can be used to measure seismic events, so like shock. And you can also use it to measure force. So that's really nice if you're trying to do something like modal analysis. We kind of tweak the accelerometers to measure a force input instead of an acceleration input. So there's three main types of accelerometers that we're going to be talking about today. They kind of fall into three categories. So the first is piezoelectric, and this is probably the most common. If you're working in a lab, you probably have something called ICP or IEPE accelerometers. This is one type of accel we're going to mention. There's another one called charge accelerometers. They're also called PE accelerometers. The second is piezo-resistive. These are DC accelerometers. And the third is something called variable capacitors, or VC accelerometers. This is mostly like the MEMS accelerometers, if you've ever heard of those. So piezoelectric is a really cool kind of phenomenon. Piezo comes from the Greek word for pressure, to squeeze. And essentially what happens is inside an accelerometer, there is a tiny little crystal. It can be made of a couple different things. It can be made of quartz, it can be made of ceramic. But when you squeeze this crystal, it's outputting a voltage proportional to how much it was squeezed or deformed. So here's a quick little animation. As the crystal actually changes shape, charge is distributed across that crystal, and we can measure that voltage output. The reason for that is you're actually changing the geometry of the atoms inside of the crystal. As you compress and put into tension, you're altering the shape. You'll get a positive and a negative charge, which we can use because, as we said, it's proportional to how it's being stressed. So it's something we can kind of take advantage of in accelerometers. The basic principle is when you have a mass inside an accelerometer and it's applying some type of force or stress, it's undergoing acceleration, the piezoelectric crystal will output this voltage, and then we will measure the voltage. And one of the reasons they're really popular is because they have really good dynamic range. That means that you can measure really well between a really low signal and a really high signal. They're very linear, and they're pretty good over a long range of temperatures. Not all temperatures. Obviously, there's an upper limit, and depending on what type of accelerometer you're using, some have higher temperature ranges than others. But typically, these are pretty solid, and they're not going to drift a lot over time. So calibration on these is much easier as well. So inside an actual accelerometer, this is what it would look like if you were to take a section view. We have this seismic mass, and that seismic mass is what's going to stress that crystal to output that voltage signal that we want to measure. Then there's something called a preload ring, and what this preload ring does is it applies a force to the accelerometer that makes it really rigid and forces it to be linear. When we say linearity, what we mean is that the accelerometer is actually measuring what the signal is supposed to be. So for most accels, they will measure lower frequencies pretty well up until a certain point. And then when you get into high frequencies, you can see that this is in dB. Sensor number 2 can't measure up to high frequencies, and sensor number 3 starts to drift. It's actually outputting a reading that's 2 to 3 dB higher than the signal that you're measuring, which we don't want. We want everything to be flat. We want what we're measuring to be what's actually being produced at the signal. So it's really important that these accelerometers are linear. And if you ever purchase an accelerometer, you can check a spec sheet and it will tell you when you get one what your accelerometer is linear up to. So this is something you need to keep in mind. If you need to measure beyond like 10,000 hertz, for example, and you want it to be really linear, you have to buy a very specific accelerometer for that. If you're really interested in low frequency or 0 hertz, there's a bunch of accelerometers that are specifically designed for that as well. We've got this piezoelectric crystal, we've got a seismic mass, we've got a preload ring, and then the important thing, this is an ICP accelerometer, and the way you can tell is it says it's got built-in electronics. And ICP, it stands for Integrated Circuit Piezoelectric. This is actually a trademark of the PCB company that produces accelerometers. If you want to get the generic term, it's IEPE, and it stands for Integrated Electronics Piezoelectric. And the integrated electronics is really the key point between the charge accelerometers that I mentioned earlier and these ICP or IEPE. These ones have the electronics built in, and that's going to be a huge advantage, a lot of applications, if you're trying to measure acceleration. So a couple things about these IEPE sensors, or ICP sensors, they're the same thing, just one of these is a trademark, is that they require constant current. Because there's integrated electronics inside of the accelerometer, we need to power those electronics with this constant current. Most of the data acquisition systems that you have, especially if you're using SCADAS, will have ICP-powered availability, so you don't have to worry about that. So the integrated circuits are inside the accelerometer. They're low capacitance quartz usually. Some ICP sensors can be made of ceramic, but typically they're made of quartz. They're low impedance sensors. This is really important because there's a huge difference between the charge accelerometer I'm going to talk about and this low impedance sensor. They're typically used with voltage amps. They can't measure static acceleration, and when I say static acceleration, I mean basically gravity, something that's being applied to you all the time, that's at the 0 hertz frequency line. But they can have TEDs. If you've never heard of TEDs, it's called a transducer electronic data sheet. So TEDs are really cool. What you can do is you can actually program the sensitivities inside of the accelerometer. And then in test lab will read TEDs. You can click read the TEDs, and then it will actually tell you the manufacturer, the type of transducer, the serial number, and then more importantly, what people use it for is the calibration factor. And because, like I said, these accelerometers tend to be very stable, they don't drift a lot over time, you don't usually need to calibrate them very frequently. This can be really useful in saving you time in your lab setup. For ICP sensors, there's a specific type of signal conditioning. And when we say signal conditioning, what we really mean is we're trying to get this voltage signal here into something readable at our system. So for an ICP sensor, if you have an instrumentation that has built-in power, that constant current, you don't really need anything special. You can just use a coaxial cable. This saves you a lot of cable space. If you don't have a readout instrument that can do ICP sensing, if it cannot supply that constant current, that's okay. They make signal conditioners you can put in between. The only problem is for every single signal channel that goes into here, you have to have another one that goes into here. So you're effectively doubling your cables. And this is really important because these sensors are low impedance, which is really nice. It makes it easy to measure. And because it's low impedance, we can have high impedance measurement systems. So all the voltage that's in this circuit is going to stay in this circuit, not going to go into our measurement system, which we wouldn't want. And if this was a low impedance system, which they're not designed to be, then we would get some voltage errors between them. But if you're doing signal conditioning for an ICP sensor, 9 times out of 10, you've got this built-in ICP power, and all you need is a simple cable to connect between the two. That's not always the case. We'll see that with the charge accelerometers. This is a big advantage of ICP over those charge accelerometers. Okay, here's that cable management picture. If these were all ICP, but you didn't have something that was able to supply that constant current, you would need that signal conditioner. And for every single cable that you plug into your measurement system, you have to double the cables in the signal conditioner. If you're measuring a lot of channels, that becomes very cumbersome. Here's a fun, beautiful picture on what cable management can look like for a lot of engineers if you have the right system, at the best of systems, I should say. So charge accelerometers, these are called piezoelectric instead of IEPE. And once again, that IEPE is the integrated electronics. The main difference is that this has absolutely no integrated electronics. So this is able to output a charge signal. That's what we're measuring with the charge accelerometers. Instead of putting it out in millivolts, it puts it out in coulombs or picocoulombs because it's really, really small signal. But it doesn't require any external powering. So you know how we have to apply that constant current to an ICP accelerometer? With charge accelerometers, we don't need to do that. We could take a cable, run it right from the Excel, and put it right into the data acquisition system. There's some caveats to that, but that's the general principle. There is absolutely no internal electronics. And because there's no internal electronics, you can use them for high temperature applications. So like if you needed to measure inside an exhaust system, for example, you could use a charge accelerometer. Makes it really easy because then all you have inside is the ceramics, and the ceramics are high temperature materials. You don't have to worry about destroying those electronics. The downside is that because that signal is so small, it's really susceptible to something called the triboelectric effect. One interesting thing is if you were to hook up both an ICP accelerometer and a charge accelerometer and you were to measure the same thing, you would measure 180 degrees out of phase. So here's the big caveat if you're going to use a charge accelerometer is you need to use a charge amplifier. So unlike the low impedance system that the ICP accels or IEPE accels are, these are actually high impedance sensors. They have a very high resistance, and that has to do with the actual physical makeup of the accelerometer. So if you're going to use it, you need to have an amplifier to amplify that signal. And amplifying that signal can be difficult. If you're using SCADIS, we make special cards that will amplify the signal that have the charge amplifier built into them. They're called VCA cards. If you're not using a SCADIS, you have to use a separate signal conditioner that is specifically designed for this type of procedure. But you have more control over your accelerometer if you're using a charge accelerometer. ICPs, all those internal components are built into the accel, so it's a fixed voltage range. They have 5 volts voltage range, and all the amplifier components are fixed as well. If you're working with a charge accelerometer, you get to bring in your own charge amplifier, so you can change the phase and gain and all those properties of the amplifier, so it gives you more freedom to be able to control it. So here's an example of if you wanted to find what the sensitivity is. If you've ever seen an ICP, so that regular accelerometer, the common one we were talking about, most of the time the sensitivity is given off in millivolts per G. But here you'll notice it's in picocoulombs per G. That's what the sensitivity is for charge. So if you have a sensitivity of 10 picocoulombs per G, like you have a specific sensor, you have a charge converter, something that's going to convert that to a signal that you can read, and you know that the charge converter is 10 millivolts per picocoulomb, and you're expecting an output of 14 Gs, you can just quickly multiply across 100 millivolts per G times 14 Gs, and see what the expected output in voltage on your measurement system will be. This is one way to kind of double check that what you're expecting to get is what you're gonna see. And if you're ever doing this in test lab, most people in test lab have probably picked the specific type of coupling, and this one has called a charge couple. And you'll see that it defaults to picocoulombs. If you're using ICP, which we will today, it'll default to millivolts. If you want to use a charge accelerometer, you can use it sort of like an ICP accel by using what's called an inline charge converter. They're sold by a bunch of different companies that make them. This threaded edge is what connects to your sensor. It's got to be really rigid, so that's why it's threaded. You know, you just saw how sensitive those connection points are. And then the B and C will go to your data acquisition system. So the signal conditioning for a charge accelerometer looks a little different. You either have a super high impedance readout, because we always want our measurement impedance to be higher than our sensor. And I mentioned earlier that this sensor is already really high impedance. You want it to go from low to high when you're measuring. So you have to have either a really special system that's designed to read these signals, and then if so, all you need is that special low noise cable, or you can have some type of voltage charge amplifier in between. So you can have a special low noise cable. This will connect to the voltage amplifier, and then the voltage amplifier is boosting the signal. You can connect it with a regular cable to a typical readout. So there's 2 things you have to have. And it's just like the other thing. If you don't have a proper signal conditioner, there's going to be an intermediate step between them. Because we're working with high impedance, we typically use charge amplifiers. If you're working with those ICP accelerometers, they typically use voltage amplifiers. And that's just because what they're outputting a voltage signal. These are both the 2 types of piezoelectric sensors that we've gone over. And then, like I said, there's pluses and minuses to each one. The IEPE, that's the integrated electronics. These are good for if you have really long cable runs. Obviously, we saw what could happen if you had long cable runs and there's a lot of noise. So this is good for long cable runs in dirty environments because these connections don't need to be as secure. This has a built-in self-check inside because it's got that internal electronics. So there's a bias voltage that it'll check for to make sure that the accelerometer is working. It can be used with TEDs. This type of accelerometer cannot be used with TEDs. There's no integrated electronics to put that information in. It contains the signal conditioning internally, so you don't have to worry about it. Lower cost per channel and lower output impedance, which makes it easier to work with. Charge sensors are better for shock measurements if you don't know what the shock range is going to be. They have to be used with that special cable, but they're really good for high temperature environments. And this is, I would think, what most people would use a charge sensor for, or a piezoelectric, regular, non-integrated electronics. It does require that external amplifier, and it does have that high output impedance, which can make it a difficult sensor to work with. But all things considered, if you're looking for something above 400, 500 degrees, if you're working in like a really high environment, you probably are going to want to use a charge sensor. So DC accelerometers, these are piezo-resistive. That's that second category. And by piezo-resistive, we just mean that when a material is being stressed, the resistance of it changes. And if that sounds familiar to you, like a strain gauge or some type of Wheatstone bridge configuration, then you're in the right ballpark, because that's exactly what we use to measure piezo-resistive accelerometers. It can measure dynamic and it can measure static acceleration. And you might need to measure static acceleration if you're particularly in the aerospace industry. That would be a really good application for that. DC accelerometers will read 1G if they're placed properly, whereas ICP will read 0. And it's important to note, I said placed properly, so like for example, if you were to tilt one of these accelerometers on its side, then it would read 0. But if it was a single axis accelerometer, my little single axis accelerometer, it would measure the acceleration due to gravity. The main difference is it requires that DC excitation. What it's going to actually be doing is it's going to be seeing a constant DC voltage signal and then measuring how the resistance changes over time as a result to stress. Let's say DC. So this is different than the voltage that we're measuring as an output from the piezoelectric crystal. Here we're measuring the change in resistance. So it needs a constant DC current applied to be able to see how that's deviating. We're pulling that out of the circuit. And that's one of the reasons why it's able to do both, because it has both components. But typically they're made up of some type of metal strain gauge or some type of silicone Wheatstone bridge. And the way that most of these function, a metal strain gauge not connected to anything obviously won't measure anything. It needs to measure the strain of something. So typically inside one of these accelerometers, you've got some type of strain gauge that's around a cantilever beam that's connected to what's called a proof mass. You'll see that a lot. And as this mass is moving up and down, it's going to change how this strain gauge reads. This mass is obviously going to move up and down proportional to the acceleration, and you can get the DC acceleration out of it. This is somebody's idea for one. I don't think that they all look like this. And one thing you'll notice is that the internal components, I'm going over the basics, but the internal components of every accelerometer is going to look a little different, especially depending on the company that made it. So don't expect to crack, a DC accelerometer open and see something exactly like this. But here's kind of like another Wheatstone bridge configuration, and then the proof mass here and a sensing beam. And as this proof mass is moving up and down, these resistive elements are going to change, and we're going to be able to measure what type of acceleration we're dealing with. If you're going to use this with a Scatus, we have a VB8 module. This is really good for crash and shock applications. It's good because it's very steady. There's not a lot of internal components that can be damaged. And also, like I said, it has both that dynamic and that static component. They're not that much more difficult to connect to a system because we have DC coupling built into the SCADA system. The last one that I want to talk about is variable capacitance. That's that third type of accelerometer. So the idea behind a variable capacitance accel, it's sort of like a DC accel, but it's got two parallel plate capacitors that work in differential mode. So what that means is it's got these two capacitors here, and what it's looking at is how the signals change with respect to one another. So here we've got this little movable electrode. It's connected to a mass spring damper system, and like we said, as this mass is excited because of some acceleration, this electrode is going to move, and it's going to move either closer or farther away from the capacitors. And as it does that, the capacitance is going to change, and we can measure that. The change in capacitance is directly proportional to that acceleration. And it's proportional because we can find out the difference between one capacitor here and one capacitor here. This is sort of how variable capacitance accelerometers work. These are most common in something called MEMS accelerometers, which is what you guys all have in your phones if you have a cell phone. They're these tiny microelectric mechanical systems. They're really, really small because they have to be able to fit inside like a cell phone application. They were kind of a huge revolution and sort of changed the way that we measured accelerometers and acceleration. They can be, I would say they can be pretty accurate, but ICP accelerometers tend to be more accurate for laboratory applications. That's not to say that these can't be accurate. They absolutely do make laboratory accurate accelerometers. But it works on the same principle. You have some type of electrode, and then you have these little fingers. There's a known mass of these fingers, and there's also a known capacitance between these spaces. And as these fingers move because of acceleration, the capacitance will change, and we can measure that capacitance change, and we're able to pull out the acceleration that way. These are almost always printed or etched. They're usually made of silicon. Because they're made of silicon, they can be made so tiny. This is kind of an example of one. So they have a tiny little like printed circuit board chip, connects directly to the MEMS, and you'll see it's a VC for variable capacitance element. So they're really nice to use if you need really small accelerometers to measure things in really tiny locations. They can also measure static acceleration. That's something, once again, those AC coupled cannot. And they can either be PR, those piezo-resistive, or they can be VC, variable capacitance. Shock accelerometers, these aren't different. This isn't a different type. I just wanted to put this on here in case you weren't familiar with them. They make specific accelerometers for everything, but specifically there's accelerometers that are for shock. They have typically lower sensitivity, so they need a higher input, which is good because that's what you want when you're measuring a shock response. And they have really high resonance frequencies. So one thing that can screw up your linearity, we talked about linearity, is if you have a resonance in this accelerometer, which all accelerometers do have, they're just typically designed to be really high, way above where you would ever measure. Shock accelerometers have resonances that are even above that. This will not affect your measurement, the resonance of your accelerometer, because it can, and that's usually not what you want when you're doing measurements. They're also designed to survive high internal stresses. So typical IEPE ones, if you're just using shock for them, you can break them, but they can be IEPE or that ICP or just the regular charged piezoelectric. Just to show how to get things set up. Okay, so here I've got a tiny little speaker. You can see that it's roughly the same size as my accelerometer. I'm going to turn this on. And then here I've got my little SCADIS unit, and it's just a cable. This is a triaxial accelerometer, and the triaxial accelerometer is connected to my SCADIS. Very simple setup. So I've opened TestLab, and in TestLab, I've gone to the channel setup right away, so I can start turning channels on. The first one's defaulted to on. I want to turn on all three because it is a triaxial accelerometer. I'm going to call this X direction, Y direction, and Z direction. This is how you would set up this type of sensor. I can put the directions in again, just for posterity and post-processing. It's really good if you have these directions in. It'll make things easier if you're post-processing. And then we're here at this input mode, and it defaults to voltage AC, but this is an ICP accelerometer, so it needs that constant current. So if I leave it on voltage AC, and I try to start measuring with it, you'll see that my signal is super low. We're not actually exciting the accelerometer. So that's one thing to notice if you're trying to, I'm knocking on the table right now, and you can see that it's not really registering any acceleration. That's one easy way to check. This is probably the first thing most people do if their accelerometer isn't working, is they forgot to turn on ICP if they're working with an ICP accelerometer. So I'm going to go back and I'm going to fix that. I'm going to turn on ICP. And you can do them all individually, or you can click and drag like in Excel. Measured quantities, acceleration. So I'm going to put in some sensitivities. I happen to know that this is a 10 millivolt per G accelerometer. Now, the actual sensitivity isn't perfectly 10 millivolts per G, but I don't have the manufacturing specs for it anymore. If you have an accelerometer, you will get sensitivity for every direction. But now that I have my accelerometer set up, I can do super quick measurements. So I've got it set to this little speaker, and I'm going to just go straight to measure. I'm not even going to worry about any of the acquisition stuff. So I'll start this from the beginning. So if you're in the measuring tab, I want to do some live monitoring of my data. I'm going to go to front back, create a front back real quick. I want to see the data. Right now, if I hit ARM, there's nothing in here. I'm going to go to Data Explorer. If I go to Online Data, go to Instantaneous. And mine, it's hard to see on my webcam, but the up and down direction is actually the Y direction. And you'll notice, because I talked about mounting, I actually put a little piece of tape and then I super glued it to the speaker because beeswax was not a rigid enough connection. This is a very tiny speaker in comparison. Okay, so I've got an auto power. I'm going to click and drag it here. And now if I start to hit play, we have some signal. I'm going to do a sweep. It's a 20 to 20 kilohertz sweep. So what you should see happening is, because it's on the speaker, and that speaker is basically a dynamic system. It's a little magnet that's moving back and forth at that frequency that I want it to. It's creating vibration of the air particles. We should be able to see a sweep, a little frequency that as it increases, it goes across. Okay, that's pretty loud. So you can see start to finish, the setup was very, very easy. I was able to look at the data and measure a very basic signal. And all I had to do was make sure that my ICP was turned on. Because the Scatus XS, the small model Scatus that I'm working with, can handle ICP-powered accelerometers.